Good afternoon to you. Bon après-midi à vous. Buon pomeriggio a tutti voi. Guten Tag. Buenas tardes a ustedes. Welcome to Paris and to the International School of Astrophysics, Daniel Chalonge-deVega, for this lecture in the program of Nobel Lectures in Physics we organize this year. And it's a great honor and it's a great pleasure to welcome here today Didier QUELOZ, Nobel Prize in Physics, professor of physics at the Cavendish Laboratory, Astrophysics section, University Cambridge, UK, and professor part-time Université de Genève in Swiss. Didier QUELOZ grew in Geneva and his studies performed in Geneva and obtained the diploma de études approfondies en astronomie astrophysique à l'université de Genève. His PhD Université de Genève performed also an Observatoire de Genève, and his PhD in 1995. It's remarkable and extraordinary that for his work in doctoral thesis and PhD, he obtained the Nobel Prize in Physics 2 years ago, I mean in 2019, shared it with Michel Major, his, the advisor at that time, also a very well-known astronomer, astrophysicist in Switzerland. And the point, and the originality is that he discovered, and he got the Nobel Prize in Physics for his discovery of the first giant, the first planet outside the solar system, discovered with a very creative spectrograph, very creative and small spectrograph at the time, and the observations. We are proud to stress that the observations were performed at the Observatoire de Haute-Provence at the south of France with a telescope of 1.95 meters. An older set telescope. It was not perhaps expected, not at the time, that so creative work and outstanding discovery could be performed, and also with a small team. And I should say that Daniel Chalonge, the name of our school, was one of the founders of Observatoire de Haute-Provence and Institut d'Astrophysique till his last days, at also with that instrument, with that telescope, but with his own spectrograph at the time. Anyway, Didier performed an outstanding career, and not only, for astronomy, who provoked a real revolution for astronomy, but for equipment, astronomical equipment, new observational techniques or methods, and new algorithm, and his creativity and enthusiasm is shared and allowed him to have a center devoted for that. Is the center Exoplanet Research Center in Cambridge, who have also this extraordinary approach to connect and to have the different, to take profit of the cross correlation of different capacities and capabilities and abilities of the different departments and different fields necessary for the understanding of the formation, evolution, habitability, as he liked to also to include, and of the extraplanets, and which hopefully also help to understand our the formations of our planets and more structure. So saying by that, saying last but not least, his communicated communicative enthusiasm, energy, and humanity is a real quality we like to stress. So we are very pleased, very happy you are here today, Didier, and now the floor is yours. Please, Didier, thank you.
Thank you, Norma, for this beautiful introduction. So kind. So the idea of the lecture is to share with you the extraordinary new perspective that we have right now on our own solar system by essentially the comparison with the many systems we have found. So that's why people tend to qualify this, what is happening in astronomy, an exoplanet revolution. And as you mentioned it, there is a lot of impact of this discovery on other fields, because as soon as you talk about planet, you have to deal about the structure, which means you're dealing with earth sciences, and then you very rapidly have to ask the question of life, and it means opening a complete new chapter. So I will slightly touch upon a little bit this topic at the end, but before, I'd like to give you a complete overview of what we have learned and this new perspective. Some people have even mentioned, though we have set the next stage of the Copernicus revolution by trying to recenter, in a sense, the solar system from being a unique and a kind of a standard example of a planetary system into only one amongst many, and nothing really very strange compared to the other. So let's have a look just about the number to get a feeling what has happened. So if you, okay, here we are. If you just count the number of planets detected on other stars since 95, this is the histogram you get. So this histogram is organized by the techniques that we are using to detect them. So what you realize from these techniques is there is not, I mean, essentially two main methods is driving our understanding of the planetary system so far. One of them is the one we've been using with Michel 25 years ago, which is using the motion of the star through this change of radial velocity or change of speed of the star in the along the line of sight of the observer, and the fact that we have found a significant amount of planets on a short period. This has opened up a new chapter, which is using the transit of the planet. And here, the red are the radial velocity planet, the blue of the transiting planet. And then you see there is a little bit of orange, which are other techniques I will not be talking about. It can be used of gravitational lensing or direct imaging, because actually we have not learned very much from these two techniques so far. This is likely to change. Both are going to, I think, bring to mature and to add some new views on that, but that's not the situation right now. So I will essentially be talking about the planet that we have been detecting with these two techniques, and there's already a lot to say about just this. Okay, so that's just to start the scenery here. Now, to understand the planet of the solar system, we always have to come back to the planet of, the planet on other stars. We have to come back on the planet of the solar system. Well, there is a simple reason for that. That is the only planet that we know in a great detail, and it will remain this for a long time. So we have to accept the situation that we will have, and we do have, a very limited example of planet that we can study in great detail, but we should anyway use that carefully to extrapolate to these many systems that we will have and we have detected, but we will never be able to study with such a great detail we have on the planet of our system. So the one element that I'd like to insist, if you're not familiar with, is we have learned that there are, if you look at giant planet, these giant planets have what's called a core, a solid core. Well, Jupiter is the less constrained of this core. Saturn is pretty obvious. The way that you find this is just by doing what's called flyby. When you have a satellite, a probe that is flying, grazing the planet, you're looking at the multipolar gravity deviation, and you combine that with the rotation of the planet and the model of the internal structure of the planet to use the deviation from the spheroids to learn about the internal structure and to learn about the possibility of a core. The reason why I mention a core is because that is the main difference between a planet and a star. When you look at Jupiter, essentially you have the very same ingredient in Jupiter that you have on the sun, except the core. And that is related to the formation process of these two different objects that we're dealing with. The star comes from the mechanism, from a process which is essentially a collapsing mechanism from a cloud. This is why the mechanism is identified as core collapse, because you collapse something big, which in that case is a molecular cloud, and you form many stars at the same time. Well, the planet comes from a drastically different mechanism. That is why you have here this, the core is you don't have this collapse. You're building from the small to the bigger. So you really glue together, and this is what we call core accretion, because we accrete the stuff together. And this big difference has a lot of impact on the way we understand the planet and the way we understand the formation of the planet. But I just want you to remember that this is really the key. In the case of the telluric planet like the Earth and Mars, Venus, well, that's easy. They're essentially only made of a core. Well, then you can argue that there is a structure. That's true. There is really a bigger core and then an envelope. But that's just compared to the just giant planets seen from the broad perspective, that's what you have. Now, the other point I would like to make using the solar system, if you imagine you're flying over the solar system and you just identify the object at least with a size of 10 kilometers and bigger, you would have this picture. So you, of course, have the planets, you have then the asteroids that are familiar to us, known to us, and this asteroid belt. And then you have this amazing population of green dot here, which is a population that we qualify as a trans-Neptunian because they be on Neptune. And that was a population that was postulated. People had the idea they would exist since a long time because we had comet and cometary orbit that seems to come from this region. But amazingly, we had to wait almost about the same time of the discovery of the first planet in 92 until the population was actually detected. Well, there is an interesting historical element here because that is the reason why Pluto was demoted from a planet to a dwarf planet, because as soon as we started to detect quite a lot, because we find quite a lot of objects, one of the very famous one is Sedna, because there is a whole story around this data being stolen and all this. But then the debate of what is exactly Pluto, because Pluto was similar to this object, came, and then Pluto was demoted. Now, the point I like to make here is this is a very interesting ingredient that is telling us a lot about the history of our planetary system formation. In a way, it's an imprint of the formation scenario. And what he's telling us, well, he's telling us first the kind of size we're talking about. You see this 50 AU is 50 times the distance between the sun and the Earth here. So if you ask, what is the typical size of the planetary system? I will give you 50, 100 AU about here, essentially on the base of that kind of picture. Well, what we will learn also is it seems that beyond some distance, it's more difficult to form the planet. You have a lot of stuff that never made as a planet. So you have this idea of the core accretion. So they never had the time to accrete properly and to form a planet. And in a way, you would expect the other planetary system to look alike. And that was really what people had in mind. So we have a beautiful picture of another system on another star, but very early on, that is matching nicely this one. So pay attention to the scale here, because I will just put on the top of that, on a famous system that has been detected with the telescope ALMA and observed with the telescope ALMA, is HL Tau. HL Tau is a star in the Taurus. It's a young star, about 10 million years old. And there is a massive disk on that star. This is a picture of the disk. Remember the size before? So you see we're not very far from the size of the solar system here. So the disk, you see that, is what we call the thermal emission from the particle or solid particle, anything from a tiny 10, 20 micron object that we tend to call that dust, to the bigger object that is thermally in a situation of equilibrium with the radiation from the stars, and then have a kind of a thermal emission. So that we're talking about 70 degree Kelvin here. The background is dark because it's only 3. That's the universe. So it's very cold if you compare to a room temperature, but it's hot enough to be detected by this amazing network of telescopes called ALMA on the Chasnandor Plateau in Chile. So what is disk is telling you is they are clearly a material at this stage orbiting around, and the fact you're orbiting into a disk, that's just the natural product of the conservation of the angular momentum. You have a specific axis, which is the axis of the rotation, where everything is collapsing into mid-plane, and you end up with a structure. And if you have a close look at the structure, you're even finding that they are, call it grooves or gaps. The origin of these gaps is debated. Could well be a planet inside. Just to help you, just to help you out there here. This is about the size of Jupiter here. So it could well be that we're saying planet, but it also could be what's called ripple, from the fact you have a planet inside and you see this kind of gravitation effect to wave of gravitations that will just go and spread through the disk. So to better understand the role of the disk into the formation process of the star, we have to have a look on the side, because here we only see a tiny fraction of the disk, which is the one that is captured by the thermal emission of the dust. But the disk is also a lot of gas. Actually, there is way more gas than solid particle. And the ratio between the two is a similar ratio you have into Jupiter. You have a very tiny core, maybe 10 times the mass of the Earth, but you have 1,000 times of the mass of the Earth, which is the total mass of Jupiter. So it's a factor 100 about between the two. So gas here is invisible because there is no thermal radiation produced by the gas, but there is a way to see the gas, but I have to use another star which is famous, which is Beta Pictoris. Beta Pictoris is a star that turns out to have a disk seen on the edge. So I show you two very famous pictures, one from the Hubble Space Telescopes, when you see the disk on the edge here, and you even can see another disk, which is a secondary disk, which is related to the fact that there is a planet on that system, and we've known that there is picture of this planet. We've seen this picture. I'm not going to show a picture of that, but just to let you know, because that's not the purpose here. But what I would like you to have a look here is how thin is this disk. Well, what you do have here is not the thermal emissions. It's a visible light, so it's a reflection. It's like the moon reflecting the light from the sun, from all the tiny particles, the dust, which is reflecting the light and detected here by the Hubble Space Telescope. So it's really, really thin. The scale is twice bigger than before. It's 100 times AU here, but it's not very far. Now, what is fascinating about the systems, if I use a picture, in this case, with the same size, But when I'm looking at a completely different wavelength, which is sensitive to the gas, in that case, the CO gas, I'm using again ALMA with a specific wavelength that picking up the transition of this gas. I do have a drastically different picture, which is the one on the bottom. Well, you see right away, in terms of geometry, there is two main differences. Well, first, we don't have to hide the stars. I should have said that on the top because the light, of course, would be too bright. So we have this dark spot. In the case on the wavelength, we're seeing the star is invisible here. But the disk is way more thicker on the vertical axis, way more thicker than you had on the top. And it had also a cutoff. There is a distance where there is no disk, while here you do have a disk, right? This distance about 100 times AU here in the case of the CO. Well, if you think about that, there is very good reason for these two different nature. The vertical nature is due to the fact you have a gas. And if you have a gas, you have pressure. If you have pressure, you have what's called hydrostatic equilibrium. Well, you all have been in the mountain. If you, well, you should not do that if you are doing the mountaineering, but you throw a stone, it's gonna fall, right? Well, when you breathe, the CO2 coming out of your mouth is not going to fall. It's going to stay. There will be a kind of balance here. So the gas is balancing with the pressure. That's why you can breathe when you are when you are in the atmosphere. Well, all the solid will just fall because there is no pressure here. So the elongated structure of the disk here in the vertical axis is the reflect of the hydrostatic equilibrium, which is due to the nature of this gas. So we have far more extended here. Now, the fact it cuts off here, it's just because it's too cold. So you can take the CO, you can take the water as a gas. Well, if you cool down the water, what you're going to get? Well, you're going to get ice or snow. It's called a snow line. And there's a distance where there is no disk at all, at least no gaseous disk. So of course, it depends on the nature. First comes the water, after CO2, CO, and then you have all the kind of gas you can imagine. And it defines a structure into the disk where at that point, you had a lot of CO at the beginning, but because of the nature of the disk, the CO is on solid form. So if you think about that, there is 100 times more material available in a gas. If this material is as a sudden available in terms of solid, it means you have 100 times more solid on the mid-plane that is there. This is exactly the missing bit here. This is why we believe the giant planet has been formed farther out, because there is so many solids eating each other by the nature of this mid-plane, which is very thin. So they're eating each other, they're gluing each other, and they're forming the core of the planet. This is why we have the core of the planet made extremely quickly at a time when you had enough gas around. So of course, it has to be another gas, but hydrogen, don't worry, to transform the hydrogen into gas, you can go very cool, like very cold. It's not gonna work. So there's always a gas around. So as soon as you get enough mass from this, all these solid particle coming from this icing line, you will accrete a lot of gas, and that's how you end up with the gas giant. So this mechanism is a beautiful mechanism that explains the structure of our own solar systems. You can imagine the shock when we came up with this hot Jupiter very next to the stars, because it doesn't fit at all. So what was missing in these ingredients is still the fact that the planet may have well formed at that location, but you have a lot of dynamic into the system that is moving the planet around. And that was the big outcome of the early discoveries of planet, is to open up it's kind of a new window on other mechanisms that we had completely overlooked in the many mechanisms that are playing one after the other one in the formation process. Well, as an outcome, it's even more dramatic than it is right now, because we have not only found objects like hot Jupiter, we have found plenty of planets on short period. This is the current picture of where we stand today. I'm just looking at 3 parameters here to make it simple, but it's already telling a big story here. Well, the period of the planet, the mass on the right of the planet, which is the assumption that you derive the mass from the radial velocity effect, assuming the sine of the angle is 1 for simplicity. And then the radius of the planet, which comes from the transit. So the blue point are the transit object, the red are the radial velocity planet. Of course, some of them detected in transit have also a mass. That's why you have some blue object here as well. So there's a bit of mixing, but it's still real measurements. So there is it's a real data. It's not extrapolation from one to another one we have here. Well, you see a couple of very fascinating features here. First, there is clearly 3 groups or cluster. I don't like the word population, but cluster of planet that we do see here. Well, first, the one I was talking about, the hot Jupiter, either in terms of size. This is 10 times the size of the Earth, which is one size, which is the size of Jupiter. Jupiter, to help you, is there. And this is about 300 times the mass of the Earth, which is exactly the mass of Jupiter. But look at the period. 3 days, 4 days, 5 days, 6 days, 7 days, exactly the same here. So we have a population clearly, which is the population that was not expected at all. Now we have a couple of planets detected that seems to be like Jupiter, very poorly in transit because the transit doesn't work very well, because the likelihood of a transiting planet when the period increase is very poor, because there's a drop of the likelihood of a transit, and you need to observe so many stars to at least be lucky to be at the right alignment to find them. The transit is a poorly technique to detect this object here, but the radial velocity is much more efficient. But the big surprise you have here is we're not only detecting objects like Jupiter, we're detecting object that tends to be even bigger than Jupiter. And that opened a very interesting new chapter, is what do you define as the upper boundary for a planet? Because you can imagine here there is clearly planets which are 10 times the mass of Jupiter, and it continues up. Well, there's something we know for sure is when you reach 80 times the mass of Jupiter, there is enough pressure in the inside of this object to start the fusion of the hydrogen, and then you have a star. Well, below this limit of about 80 Jupiter mass, there is still a moment when you can have this mechanism, but not with the hydrogen, with just the deuterium. And it works until 13 times the mass of Jupiter. This is why people tend to use as a placeholder this idea that a planet, the upper boundary for a planet is 13 Jupiter mass. But practically, you can imagine that you have a core, and the formation mechanism is so efficient that you can accrete a super Jupiter that would be exactly like Jupiter, which is 20 times the mass of Jupiter. The only thing that would happen on that planet is they will have a brief moment of the life of the planet early on, where they would ignite the deuterium and become a star, and after going back to being a planet. So you see, this is where the confusion between upper mass of a planet and brown dwarf comes up, and you may have seen that or heard about this. Now, the big surprise was this population here, which is a population of objects that would qualify as a Neptune, with the only exception that they clearly have a much shorter period, and some of them are clearly have mass and size smaller than Neptunes. So that's why we come up with this idea of super Earth or mini Neptunes. And most of the systems tend to be together, not only one single planet, and they tend to be called compact small planetary system or compact super Earth systems. So they have been detected by transit a lot by the Kepler missions. And I must say that this is a gift for nature, from nature, because without this many population of planets, certainly the field will not be that successful that it is today. And frankly, the Kepler mission would have been a disaster, because Kepler mission was built up to detect an Earth-like planet, and I'll let you find out how many Earth-like planet has there and be detected in transit? None. So this population, which is impossible population, was a gift for the field of exoplanetary science, because it kickstarted the field and it opened up a diversity that we had never dreamed about. And you have the same kind of population here that detected by the radial velocity. Now, I'd like to attract your attention on the empty area here. I mentioned, I spoke already about the fact that we have no transiting planet, or very few here, because it's just the statistics. Here a threshold of discovery that is simply by the fact that the transit is a very rare event. I mean, frankly, the transit is the worst possible technique you can use to detect the planet, because you sit on the target and nothing is happening. And then for a brief moment, something happened, is a transit, and then you have to wait again for the next one. So if you want to increase your detection, you have to wait a long time. So Kepler was patient enough to stay a long time on the target, and by repeating the discovery, repeating the transit, they were able to get very, very down, and they have detected planet much smaller than the Earth, because there is so many transit that altogether, it's square root of the number, they reach the threshold for discovery. That explains this kind of regime here. Radial velocity is the same, a bit the same mechanism. The only difference is the fact that the amplitude of the effect depends on the mass, and that creates this limit here. So when you want to find a planet below this regime, the amplitude is very tiny, and it becomes challenging. But it's similar kind of techniques are related to the fact that we have not found any Earth twin. But we have Earth mass, Earth size object on a much smaller period. Now, on this diagram, there's another interesting number you can add up. It is the likelihood to have any of these systems. So to end up with this number is pretty sophisticated because you have to deal with the threshold, the systematics, but that's a number you get. So 1 to 5% of chance to get a hot Jupiter. So you imagine you have 100 stars in the sky, 1 out of 5 of them will have a hot Jupiter orbiting. 10 to 50% will have Jupiter object. This big range depends on what you define exactly. So how far do you go in terms of distance, because you start hitting the direct detections and you can extrapolate. And by seeing few, you can extrapolate of the many. And how far up are you going to go? So this is why there's a big debate here on how many objects you have. Now, the big surprise is this population of super Earth mini Neptunes, which are clearly the massive population of objects. And even by just looking at this population, we know that the solar system is not common. These are the common planet in the universe. These are the systems that you're more likely to detect when you point a telescope. So that's why right now, when they're asking me, how to find a planet, I tell them any star would have a system, because you have this rate of discovery, this rate of occurrence of a system on the planet. Now, to understand a little bit better what we're talking about here, we can combine the mass and the size and build up a very interesting parameter, which is the bulk density, which is giving access to what is called the bulk density. So in a way, this is seen as the beginning of the planetology or exoplanetology, because it's not enough that we have the planet. We can start telling a story about what is this planet exactly. So the first striking feature you have is the hot Jupiter over there. And to understand and to read this diagram, which is the size and the mass you have in, or again, same unit in log scale, we have overlay a typical structure of 3 different kinds of planet. One of them is, strictly speaking, the Jupiter structure. So if you take Jupiter and you move around the number of mass, keeping the ratio of all the components the same, you will be going along this line here. So essentially, you will have Jupiter, Saturn, that looks pretty much the same. You already see that the hot Jupiter, they lie above in this diagram. It means that the density is less, so they're more fluffy. They, in a way, they are inflated. So the rationale for that is not well understood. It may be because they're much hotter, but the true mechanism that connect the fact they have a slightly hotter, well, they do have a hotter, clearly not slightly, hotter surface to the fact they are bigger is not obvious. Or some people are arguing we may be seeing a different kind of structure inside of these objects, but open to debate, but still unsolved. Now, you go down here and you clearly have object, and you see that it goes down. It's very fascinating because you reach the mass of Neptune, and you clearly don't match Neptune, which is fine. We know Neptune has a much less gas than this planet, so you have to understand the core, and it's much more heavy because the gas are heavier there, and much less hydrogen. But you do have objects here that have the mass of Neptune that would qualify, that strictly speaking, like a giant planet. So when you get a Neptune mass, you can get a Jupiter-like planet. It's just a mini Saturn, if you want, or a super Neptune, depending on how you want to call it. Now, we have this kind of description, which is an hypothetical planet, which is what we call a water planet. So you imagine a planet made of water, only water. Well, of course, the pressure will be so high, the water will be solid and hot in the middle, but that's just to give you a picture. So this will not explain Neptune, because Neptune has way more gas, light gas, than you can have with the watery planet. But it gives you an idea that there is a lot of objects that would qualify within this regime. And then to help you again, you use the Earth, 1-1 here, and you just beef it up. You make it just more massive. If you add more mass in the Earth, you keep exactly the same structure. you rise up in the radius. And you see there are clearly planets that would match here. So of course, there is an interesting mixing here when you're talking about an object which is 10 times the mass of the Earth. It could be an Earth bulk-like, it could be a water-like, it could even be a kind of a giant-like planet. And if you pay attention to the detail here, there is a kind of a gap between the two, which is debated whether it's because these planets are very close, and because they're close, there is a mechanism when there is not enough mass that is going to produce a loss of the atmosphere, or are we talking here about a true different mechanism producing a different kind of planet that would not be qualified as a Neptune planet? So it's a very interesting topic of current studies. But whatever we talk about that, there is a clear fact that we have to acknowledge when you're talking about a planet which is 3 times the mass of the Earth, it is not an Earth-like planet. It could well be a completely different kind of planet, and even a planet that would be more like a giant planet than really a planet like the Earth. And that was a big shock because people were not expecting this. I remember discussing with Bill Borucki early on about the Kepler missions and telling him, well, you should measure the mass of your planet because you will never know what you're talking about. And he said, well, what for? I mean, when it will be about the size of the Earth, it has to be an Earth. It cannot be something else. And we have been way out of this right now. This is not true anymore. So essentially, if you don't have these two parameters at the same time, there is nothing you can say about the system. And even if you deal talking with object which is between 1 and 2 Earth mass, there's still a little bit of ambiguity here. So it's a very active field of research that trying to find out this object. So after 25 years, now we have opened up then the structure of the planet. And this is a nice summary that was produced recently by ESA that is given us the new picture, and that should be in all the textbooks right now. What is a planet? So you still have the Jupiter as an example, of course, Neptune, part of the ice giants, the Earth, but you have all the rest, which is something in between the two that we qualify as massive core subgiants. But between the ice giants and the Earth, you can have anything like the big rocky planet with almost no atmosphere, ocean planet, which is big, thick. When I say thick, I'm talking about maybe 10,000 kilometers or a couple of 1,000 kilometers thick of water, a lot of gas, hydrogen gas, or maybe a mixture of the two when you get core and then water and then gas, and it's called mini Neptune. So all this is on the stake right now. And this is a very topic where people are trying to address it. So how are we going to do that? Well, we're going to go to an additional parameters that I've not been talking about that you kind of sense here is the atmosphere. Because when you're going to observe this object, if they have the same mass, you may be facing an atmosphere of hydrogen, something a bit more mixed, water, or essentially no atmosphere in that case of this system. So how to do that? Well, we use a light curve. So if you have never seen a light curve, it's time to just get a feeling what it looks like. This is a light curve of a transiting planet. So at the time the planet goes in front of the star, there's a bit of a shadow. It will decrease the amount of flux that come from the star. It creates this transit, which is the time when you say, I got the planet. From the depth of the transit, you get the size ratio between the star and the planet. And if you know the size of the star, you know the size of the planet and then the radius. Now, there's another moment which is very interesting, is when the planet goes behind. So it's not anymore the planet in front of the star, is done because of the orbit. The planet goes behind. It corresponds to what's called a secondary event or eclipse. So if you zoom in, and that's what I do on the bottom, that are this very interesting moment, and you think a little bit about the system, these are the only moment where you only see the star because the planet is just behind. So if you want to study the star without having anything coming from the planet, that's the only moment. Well, we're using that actually to study the planet because this sets the zero level, if you want. And if you assume that the flux from the star doesn't change, anything else is the effect of the planet. In that case, you have here two effects. You have the drastic change, which is essentially the day side of the planet. So you have this just before disappearing behind the stars. The planet is showing us, the observer, its day side. And then there is a phase functions like the moon phases. And there is a moment when the planet is showing us its dark side. So we can study here the weather pattern, the dynamic of the atmosphere. And by the amount of flux you have here, you can study the emission of the planet, the thermal emissions, or you can study the reflections. So again, the star is here, anything else is the planet. And this moonlight curve is telling you a lot about the planet. We can even do more. We can look at the transit itself. The reason why, depending on the wavelength, the planet doesn't look the same exactly. So to show you that, I will use some picture from the ISS at a time when you have a transit of the moon, just to help you a little bit to understand this. This is what it looks like. This is in the visible. You have this beautiful Rayleigh scattering that makes the sky blue that you see there, that give you an idea of the size of the atmosphere that creates the Rayleigh scattering. It's about 10 kilometers. Well, if I observe now the very same event at a slightly different wavelength in the red, I don't see that anymore because I don't see the atmosphere. At 8.6 micron, I go down to the surface of the planet and I see the true rocky size of the Earth. So the difference between the two, this is the size of the Earth with the atmosphere. This is without the atmosphere. Now I can do something else. I can look slightly more in the red, because slightly more in the red at 9.6 micron, this is the ozone band, extremely strong band. This is what it looks like. Ooh, looks bigger. So you see the size of the Earth is not the same depending on the wavelength I'm observing the Earth. So we use this feature. You can use that in the great detail. You can get all the wavelength to think about it. And you can then inverse a problem and you retrieve the atmosphere of the planet. This is how we're learning, like an X-ray, about the atmosphere of the planet. And this is how we're going to find out, combined with the other techniques, what these many planets that I described before are really looks like. Now, I would like to open a new chapter on this basis. Is people are talking a lot about habitability, habitable zone. I would like to kill some idea and maybe recenter the debate here. So the concept of habitable zone, you see a bit everywhere, is a very simple concept that doesn't have any more ambition than to say that this is a region of the orbit where if you have water on the planet, the water will stay on a liquid form at the surface, assuming a given atmosphere. That's it. Nothing else, nothing more. Well, using the atmosphere you have on Earth, right now you can define a boundary. You can modify this atmosphere. If you have no atmosphere, you have a problem here because the pressure will not sustain the water. You will end up like Mars. So there's a lot of assumption behind, but that's just nothing else than that. So assuming you know the atmosphere you have in mind, you define the location. So why people get excited about that? It's because the fact that when you look at the sun, all the planets I've been talking about, and essentially all the ones that are rocky, will fit into this square. So they're all out of the game to be within the habitable zone, because we know they're rocky because we have these two measurements. No, you can extrapolate, and some people have argued, I don't need to know the mass and the size is enough. I would argue this is wrong right now. We cannot sustain any such argument anymore. We need both elements to understand, or we need additional element that would demonstrate that we are within the rocky planet kind of regime. So the problem you have is essentially it's out of the regime. So Kepler-22, I think, is not a solid evidence because we don't have the mass of that system. So we cannot claim that this is in the habitable zone because, well, it is, but we don't even know if it's rocky. So the question there is, how can you reconcile this habitable zone and look at more detail of the prospect of liquid water with this diagram, where we just look at smaller stars? Because if you look at smaller stars, the amount of flux you get, assuming again the same atmosphere, will put this many planet that we have found within the regime where it is in the habitable zone. So this is why people got a bit obsessed right now. This is why there is a Kepler mission to look at low mass stars, the so-called M dwarf, because we know that if you find a rocky planet on the M dwarf, like there are some example here, then we get the mass, and then they are within the habitable zone. So it's a very interesting concept that people are using, and a lot of focus is going right now. So I want to mention only one example here, which is very extreme, very famous, is TRAPPIST-1 system. TRAPPIST, the orbit of the TRAPPIST it's an amazing system. It's 7 planet in transits. The fact there are so many is because the system is extremely close to the star. So the planet H of TRAPPIST, the orbit is the same as 51 peg, which is 5% of the distance between the Earth and the Sun. The reason why the system has some of these planets within the habitable zone is because the star, the temperature of the star is only 2,800 degrees and not 500, 700 like it is for the sun. So you have a kind of a rescaled version or shrunk version of the solar system. And that's why it is pictured on this diagram. Is the orbit is essentially there, but because of the fact the star is very different, it's much cooler, then you have a situation where you can have a couple of them actually into the habitable zone. Well, are they rocky? Well, we got lucky because the system is in a full dynamical resonance system. It's called two cross Laplacian tree system here, triplet systems. So there's a lot of interactions called TTVs or transit timing variability. This is all the variation we have. We've been observing the system since now almost 3-4 years, and you see the change for each of the planet D, and then you can model that. There's a very recent paper of Magel on this, and you can use that to constrain the mass of all the planet. And then you end up with this, where the system is essentially not far from being a solar-like system. So that's why we do believe we are here facing a rocky, 7 rocky planet. And an excellent target maybe to look for atmosphere, within the idea that the fact they are rocky planet doesn't tell you the whole story. It only match within some error bar, and there's still a bit of regime to have a kind of a thick atmosphere. When I say thick, without being really visible on that kind of diagram we're talking about. Now, I would like to open up a chapter because it's something I'm doing since a couple of years, is following this many detection of planet into the habitable zone. The world becomes a bit crazy about life on this planet. And with some of my colleagues, we've been trying to approach the problem in a complete new way. And I would like to share with you kind of ongoing thoughts about how to look for life and how astronomers are trying to get into this game, combined with other work being done elsewhere, combining chemistry. Well, I like to take a provocative statement. Is there a life to be expected on TRAPPIST-1? How can we understand that? Now, the question is an open-ended question, because when you talk to biologists, they tend to show you this kind of diagram. A life has to be a kind of a system that include 4 ingredients that have to work together. There's replications, there's some way to have a metabolism to create, to repair, some way to create the energy, which is a kind of a mechanism, like metabolitist, catalyst mechanism that you produce the energy, you're able to make the stuff, and then of course you have to be protected. This 4 element together is the definition of the biological element here. But this definition is very nice. I understand that for the biology, but practically for astronomers, what could you do with that? There's nothing to do with that. So astronomy tends to have a complete other view on that, which is looking at the systems. And what could you say about looking at the systems? And they come with this kind of diagram. When you look at the feature into the atmosphere, this beautiful series of pictures from Wikimeadows here, trying to kill the idea that when you have water and oxygen, you have life. And this is absolutely wrong. We know that. If you still believe that, it's time to stop believing that, because Vicky demonstrates with 4 other cases that you can easily produce water and oxygen and ozone by complete different mechanism, just by the chemistry. Remember, water is just hydrogen and oxygen. There is plenty of oxygen and hydrogen everywhere. Oxygen is a byproduct of formation, stellar formation. Hydrogen is free for use, almost infinitely free for use in the universe. So putting the 2 together, you get water. So there is nothing special about water. There is plenty of water. When you point a radio telescope anywhere, you find water. So we should really kill this idea of trying to believe that once you have water and oxygen, you find life. This is wrong. Well, if you find a copycat really of the atmosphere of the Earth, yes, in that case, because there's much more, the CH4 and then CO2, there's a lot of rebalancing here that comes into play. But frankly, accounting for the diversity we have right now in the planetary system, do you really expect the planet to look exactly the same? I mean, this just doesn't make any sense to me. So I think we should open up a bit our mind and trying to come up with a perspective that is connecting the biology way with the astronomers way. And how to do that? Well, let's try to use a physical approach that is in a way a bit inherited from what the people have been doing to understand the nature, by rebuilding trying to build the origin of the matter by building a kind of standard model with a formal ingredient that you can assemble. So if you look this way, what is the building blocks really of life? What is the start of the game? Well, you have to go back to what is called chemistry before life. This is called prebiotic chemistry. And the prebiotic chemistry, I think, is sending us a signal, and we have to start from there. And the signal of the prebiotic chemistry is we have a very simple ingredient, which is the kickstart of life, that is used by any life that we have on Earth, which is the amino acids. It's 20 amino acids. Well, you can argue it's just a piece of luck. And as a physicist, I will argue the opposite. There's a good reason why is that. Let's try to work from that amino acid perspective and try to build up a complete model from bottom up. In a way, let's try to make life. Because the day you can make life in a lab that is realistic enough, you will have demonstrated it's going to work. But until you do that, by comparing structure like is being done by the origin of life on the bottom of the ocean, I think this is dangerous, because you do kind of prerequisite having an end product, you're trying to find matching. While in this case, you don't match anything. You're trying to rebuild from the first principle, what is the ingredient? So the idea here is recently there has been a significant progress, not from the astronomy side, but from the chemistry side. The famous paper, 2015, that assemble a couple of very fundamental ingredients, which is water, SO3, which is a byproduct of volcanic activity, HCN, this is one of the ingredients easily that you can find in comet, and you can easily produce by impact of comet. It's not something you would believe that is related to life, because this is a deadly gas, HCN, cyanuric acid, but it seems to be critical here in the series and quite common in the solar system. You take an atmosphere, which is quite what you would expect from the planetary system as being formed, which is slightly reduced, which is a big difference from the work being done in the 60s and 70s when people trying to reproduce life, because they were using extremely energized atmosphere, highly reduced atmosphere. We don't do that now. It's very neutral atmosphere, which is what you expect. It's a CO2 essentially atmosphere in the planet. But the big stuff is where do you get the energy to make the chemistry? You know, if you are a chemist, there's two things you need to do if you want to have the chemistry, or three things working. You have to eat, you have to shake, or you have to beam with UV flux. That's the only way to make the chemistry happening. So in that case, we decided that UV was a good idea because they are UV at that time, because the sun is there. So when I met these people in the chemistry building this model, they were arguing that UV is key for the mechanism and they need UV. And I asked a very simple question, a very stupid question. I say, oh, does it work with the sun? And they stare at me with big eyes. They say, we have no idea. We have no way to compute that. And then we started the long-lasting collaborations. We have recalibrated. We went into this lab, calibrated the UV lamp they were using. Now we have rebuilt a quite new equipment that is producing a real star that can control, and trying to find out whether the chemistry works. Because what they came up is chemistry is always working. When you play with chemistry, it's very easy to end up with something. And the real issue when you form life is not making the chemistry working, is making the chemistry dominating. Because if you don't dominate the chemistry of life, you end up with beautiful molecules, but they're making perfumes, or they're making something which is completely useless for life. So you have to produce the ingredient of life. And that was really the idea here, is the mechanism of this 20 amino acid, or capturing all the ingredients. If you beam enough UV flux, that it works. Otherwise, if you don't beam enough, it's not making the amino acid. That's a fundamental paper in 2015. And I'm pretty sure that in the next 20 years, this mechanism, I think, will be fully proved. And then the people behind the paper will get the Nobel Prize, because that's a very serious reason why to explain the origin of life. So what we did, we just tried to test that and bring the UV flux calibrated. And we came up with this new concept called abiogenesis zone that comes on top of the habitable zone, that demonstrate that there is a minimum amount of flux, which is here, this region red, this region here in yellow, that is needed to make the chemistry working. And we were shocked to realize that it only works on the top of the diagram, which is exactly the kind of temperature you have here for the sun, and with distance with about 100 days. So essentially what this is telling you is if you have a star, a rocky planet orbiting an M stars like TRAPPIST, it is in the habitable zone, but there is not enough UV flux to produce this amino acid. So it doesn't say there is no life, but it just says that it's certainly not the life as we understand it. Now, if you have a slightly bigger star, doesn't need to go to the sun, but can be a little bit like a late K star, a K dwarf, or a JK star. With something like Venus, for example, that would work. So that makes enough flux to produce the amino acid and as a key ingredient. Of course, amino acid is not life, but at least it defined the key ingredient here. And that opened up a complete new horizon to me and of collaboration, because I start talking with my colleagues of Earth Sciences, and I ask them, what do you think about that? And they come up with a very complex model of that kind and say, oh, that fits very well into a global scenario to form the Earth. And from the astronomy perspective here, when you start the planet, then you cool down the planet. There is the atmosphere enriched, and then there is the volcanic activity, the UV flux I was talking about. You produce the prebiotic of life, and then you start life, and then you start to completely change the nature of the atmosphere. So we start building up this kind of massive modeling here, trying to bring all these ingredients together, assembling the astrophysics perspective here, which is key, because you have to form the planet, you create the structure of the planet, and then the planet has a life. The atmosphere is changing. You can even imagine a massive event that is completely going to remove the atmosphere, and you reform the atmosphere. And then there is even what's called a late veneer, which is you polish really this atmosphere by bringing other ingredients, and this is mixing up with the volcanic activity that doesn't start right away, and you need to create the magma and the partial melting to start this mechanism as well. And ideally, you would like to see some traces of this volcanic story on the atmosphere of this planet. So all this is a big picture. And if you talk about life, we will have to go through that. So I think we should stop being naive about looking for life. I think we should start seeing that as a global program that connects all these dots together. Well, you will only understand what's going on there if you understand the various stages, the formation process of life. So I would like to share with you my last thought about how we're going to do that by using a very simplistic diagram, the kind of diagram that as a physicist I like, because this is very simple, much more simple than maybe the biology mechanism of life. Well, let's imagine you have the complexity on one axis and you have the aliveness. I will not say more than aliveness. Well, one reason why I say aliveness is I believe there is something that getting alive by steps, and there is a regime where there's a threshold. Well, essentially, you would qualify as being alive. Why would you do that? Because essentially it takes control by evolution. So this is where the biology begins, and this is then story of the complexity of life as soon as you have it. But before you reach that, you have to go through a process, and this process is a combination of many different fields that have to play together. Astrophysics is the kickstarting with the geophysics, with the origin of the system, and these two people have to talk together. These two teams have to talk together. Geophysics has to deal with the prebiotic chemistry, because whatever you like it, prebiotic chemistry is not going down, is not going down in a wet lab. It's going to be down in dirty lab, which is called surface of the Earth, or pond or lake or river or anything that you can think about. Anything you can think about thinking about now the probe, which will be probing a kind of a system that some time ago had clearly water, and that's why it's very exciting, this idea of the Martian mission right now. You have to move from prebiotic chemistry to something bigger. It's still not very clear. There are a couple of papers on that, is building the macromolecule, and then the macromolecule got self-replicated with enough repeatability at some point, and they're becoming life. And this mechanism is a very erratic process, because there will be innovation, and there will be also consolidations. And altogether, it's extremely difficult to predict all the path, because something can help. But the whole idea here is, if you want to understand this, we have to discern all the chance. And I think the reason why we have failed so far, and particularly with the astrobiology, because we're trying to go one bridge too far. We're trying to connect the physics, astrophysics, with the biology. And it's extremely difficult to do that if you don't build the step in between. So right now, the field is restarting a little bit to get reorganized, where instead of trying to make the big jump between the two, we're trying to go by step and by stair. And I think the exploration of Mars is exactly along the direction. So they've been very careful not to claim they will do that, but they want to study geophysics. They hope to find some traces of some chemistry, and hopefully some traces of some macromolecule. Are they going to find some more advanced traces of fossil or anything of life? I don't know, but certainly they're going along the way of this kind of diagram here. Thank you for your attention. I will stop here and answer some questions.
Thanks, thanks so much. Thanks so much, Didier, for this very clear, outstanding. I mean, in the approach, we like. I mean, and a real synthesis. I mean, in a very complex, field. So you open. I mean, you open. We learned. I learned a lot. A lot on the subject because you put it in an updated synthesis. And let us now open for questions, comments. Let us open the discussion. So please, participants who like to address comments or points, please raise your hand. Activate the microphone. I don't, so please. I mean, it was very clear, and so are there points? If not, I will just to start to comment on to ask Didier. So. Now, with your, I mean, which kind, one of the, I mean, about perhaps the first chapter, because you very well organized it in different chapters. Which kind of observations or instruments are you using? I mean, what in your programs, or what do you think? Is the best, I mean, for you to track, on to discover, on to bring more understanding in what you are thinking about to advance in the field.
Well, there are a lot. Yeah, I understand the question. There are really a lot of different approaches that are going in parallel. Well, first, we have to acknowledge the fact that despite the transit may not be the best system to study planet because they're very rare. And I used to say for 1,000 planets, you only have one transiting, roughly. It's still the most efficient way right now to study in great detail the planet atmosphere. And there is a series of very ambitious missions and programs that are going to use the transiting planet to study in great detail the atmosphere. So, of course, people are detecting transit these days. There are test satellites. We do follow-up with the Kerbs satellite transit in great detail. There are ground-based programs using very high spectrograph to study features during the transit, and there will be the Plato survey sooner or later, and there will be the Ariel mission targeted to do this kind of atmospheric spectroscopy I was talking about. So this is going to keep the astronomers very busy for the next 20 years, learning a little more better in this kind of gray zone I was mentioning, all these many planets we have between the Earth and Neptune, and hopefully we'll get a better understanding on the formation mechanism which are leading to this great diversity that we are seeing. Now, in parallel, people are fully aware that when you'll be talking about the smallest planet like the Earth, the transit will not work. For a very simple reason, if you compare the size of the atmosphere of 10 kilometers, again, the size of the Earth, you will end up with just a very marginal effect. So the transit is a very tiny effect, and the only way that you can really make progress and to study this subject will be what we call the direct imaging technique. So we need to push this, and there is a tremendous amount of effort right now, especially with the new generation of telescope and the future generation of space missions that are going to address this, trying to expand on the work being done to essentially bringing more and more direct detection of the system. So we'll start with a big planet, bringing the radial velocity Jupiter with a direct detection of Jupiter, not only the young stars, but also the more older stars, and then going down and down with mission like LUVOR and LIFE and people are talking about. So this is really a long-term vision, but this kind of program needs to start very early on. When you think about James Webb Space Telescope, that started essentially at the time Hubble Space Telescope was built, not even launched, but built. It takes 40 to 50 years to build a mission of that kind. So we're thinking about the next, what comes after James Webb Space Telescope, which is essentially a mission built for cosmology, which has been redirected partially to study atmosphere of planet, and will do a very good job. But I think we can do way better, way more with the future generations. So I can really predict that the next big mission will be emphasis on the exoplanet on the basis of the many discoveries and detection we really have. So this is really effort going on. On the ground, there is no significant effort trying to detect this Earth twin. I'm leading one of them, and the idea is to use the capability of this amazingly precise machinery that we have built, combined with a very sophisticated analysis of the data to get rid of the intrinsic noise or variability of the photosphere of stars. So that's a bit what is going on, and all this is being done in parallel with the support of the theory of development being done by the geophysicists, trying to understand in great more detail on this rocky planet and trying to predict, trying to build up this knowledge base, expanding the model they have on Earth on bigger Earth. I mean, right now, the Earth, the model we have on Earth are extremely poor. So we need really a more sophisticated modeling here. At the time, we will be detecting traces of volcanic activities, and how far can we predict this? What is the ingredient that create this volcanic activity? It's an essential ingredient for very likely for the origin of life. So all this is kind of going on a bit in parallel, and there is no a clear build-up mechanism where people are trying to assemble forces for a bit of different disciplines. So it's change a bit of gear because it needs a lot of openness to try to read. When my colleague chemists are showing me some diagram, I have to go back as a student to understand what it means. And I think they also have to understand a bit better what the astronomers can deliver to them. The level of detail they would expect will never be there, but they have to get used to at least to the not the level of detail by the possibility of the diversity of the planetary system or the planetary atmosphere that we're going to study. It's a bit of kind of an overview what's going on.
I have a question. Can I ask a question?
Yes, please ask your question to Didier.
Yes, thank you. Good afternoon. My question is related to obviously your presentation, but also your findings of what you ended up with the Nobel Prize, and this is regarding your hot Jupiter. My question refers to the stability of the system, because you mentioned rapidly the distance from the star and the exoplanet. In the case of the Pegasi B, which is, I guess, the exoplanet you discovered, I can see that, and I watched and I found on the internet that this was very close to the star. That's the first point. But my question is, because it's quite a sizable gaseous planet, half of units, how can the system be stable? Because the mass of the star I found is one mass, more or less one mass of our sun. So if you have a very close, very large gaseous planet that is so close to the how was it studied at that time? And do you have any comment on this, on the stability?
Yeah, well, I do, yeah, of course, because that was
it's an interesting point. Yeah. Not exactly with your presentation, but very close.
No, sure. Thank you for the question. So this something we addressed in the paper. That was the first concern about is it possible, just in terms of physics. So there's two mechanisms you have to address when you ask your question. The first one is the planet too hot in a way? Because you will have a very hot planet because it's very close, hot enough that you would have enough energy, kinetic energy in the gas, that you would lose the gas. So in a way, you would kind of peel the planet away. You would just boil the planet, and the planet is just impossible. Actually, when you do the computation, you realize that it's not enough. You need to be, I think the mass of the planet is massive enough to retain its gas against the thermal energy because the gas is hot? That's the first question. The second one is related to the tides. Because you're very close, you have tides. The reason why you have tides is the fact that you have an orbiting planet. It's a bit like the moon. You will change a little bit the shape of the planet, and the planet will be slightly asymmetric. And because of the asymmetry of the planet, you will create a torque, and you will exchange angular momentum. Now, formally, this is the tide is only relevant if you have a torque. And to have a torque, you need to have some kind of, let's say, delay into the dynamic of the atmosphere to create an asymmetry. Well, the delay depends on the nature of the orbit and depends on the rotation of the planet. It turns out that when you work through the math, you realize that the planet is exactly in the same configuration than the moon. It means it is synchronized with the orbit. It means there is one hot face that will always be facing the star. So the fact that the planet is synchronized with the rotations prevents to have a massive tide. Otherwise, you do have this tide. Now, what is left over is the asymmetry of the orbit. So if you have a little bit of eccentricity into the orbit for some reason, that would be a way to change this. No, there is no obvious eccentricity into the systems. And when you assume the typical nature of a planet like the Jupiter, there is not enough way to produce, there's a little bit of asymmetry always, to produce a significant tide to migrate in essentially the planet. And if the planet would be closer, that would be, and we do have a Jupiter, hot Jupiter, on slightly younger star that are even closer than Jupiter. And we know one of them is WASP-19. If you know the name, you can Google it. WASP-19, you will see that one. We're pretty sure, I don't remember the time scale, but in 500 million years, the planet will be gone because the tide is significant on that planet to create this. That's a very good question. And we look at that because when it was the first thing we looked at and to make sure it makes sense.
I understand.
Yes. Thank you for the question.
So you are welcome. Thank you, sir.
Thank you. Thank you very much for this, also for this very, very clear key explanation, Didier. So other points, other questions, comments? It was very, so we have Peter Birma from, I think, Max Planck and Bond. I think you are in Bond, Peter.
We are stuck in Bonn. Yes, I have the question about the counter effect of making life, because if the level of cosmic ray particles is too high, then life will be destroyed and you cannot make life. And that means effectively that significantly earlier than on Earth, life could not be formed anywhere in the universe. Because the cosmic ray level was too high. And is that taken into account in your calculations?
Right. The only thing we've considered here, and I've been very careful, you know, if you look at the way I've presented it, I have never said that we would make life. I just would say that we would create the prebiotic condition for life. It happens that the prebiotic condition, we're talking about this prebiotic chemistry, there is no impact at all. What you're talking about here, that would be relevant for the UV flux as well. It's the weak bond when you're talking about the H bound of the DNA or this kind of stuff. And then this would be destroyed for sure. That's how you then use to kill germs, you use UV flux. So UV flux, anything like that, would clearly destroy life. So there is a step that you need to go through from the prebiotic chemistry into a situation where you anyway have to protect yourself. And I think the cosmic ray is the least of the problem because the UV flux you're dealing that is needed according to this to create the prebiotic ingredient is killing anything that will be like a structure, DNA, even if you think about a proto-RNA, whatever, it would just be completely destroyed. So we need to find a mechanism. There is various ways for this. One way is you can imagine that by going a little bit You don't need to go very deep into a lake. You will be protected, partially protected. You can imagine that this cosmic ray that you mentioned, well, we don't really know whether the cosmic ray was, how significantly more intense it was in the story of the formation of the planet at the time you have the formation of life. It's not very clear to me. I never saw really something very clear on that. It's pretty clear that there's a lot of infall and falling stuff at the origin of the formation of the systems. So how far the cosmic ray is preventing? Well, in a way, we already have the answer. It didn't work to prevent it because we are alive. So whatever you imagine the cosmic ray may be, it didn't prevent life on Earth. So there must be a way out of that. And clearly arguing that the cosmic ray prevents life is wrong on a single basis that we have life on Earth.
Yes, but to conclude, the point is that earlier, when we know cosmic rays were much more intense, and in some other galaxies, cosmic rays are like 1,000 times as intense as here. So in such other galaxies, life couldn't form. And earlier than on Earth, everything was more active by a large factor, really a large factor. So earlier, significantly earlier than Earth, cosmic rays were way too high. So you're absolutely right. But that's why the argument on the base for cosmic rays is we could form because cosmic rays level was low enough and actually helped a little bit. You have a little bit more mutations, and then that helps your diversity and evolution too.
Yeah, thank you. Yeah, interesting.
It's another point. Thank you. Other questions or points? And just well, to my last point. 2 points. One is how much, do you think, or are there programs to go to higher redshift to reach it now? To go more in said cosmological scales. It could be possible, to start to learn or to correlate what we know from observations at higher redshift. To find exoplanets also in some more distant systems.
Well, it
could already be very interesting. There are, because
I know people are, I think, already finding planet on other galaxies is quite challenging endeavor. Well, it would be interesting. Well, look, I think the physics is the same everywhere. So
yes, that is why.
So I don't expect anything significant happening going to another galaxy. No, of course, when you go back in time, it's a completely different story. But then there is just a practical element. I don't really see how we can do anything because it's already difficult enough to just learn very basic ingredient about the origin of the galaxies and the origin of the universe, which is a very simple problem to solve because there is very few equations to deal with. When you're talking about formation of planet, which is extremely complex because it includes a change of scale, which is billion scale, and pressure and temperatures of different layers, going from gravitations to chemistry and then solid surface and all the different kind of physics. So the possibility that the branching scenario you can end up when you form a planet is almost infinite. So I don't think we need to have a look at another galaxy to experience the diversity already, which is available in our galaxy already, looking at different region with exposed at different time or different density. I don't see the push right now at that time. It may come maybe later on, but right now I think the focus is trying to do what we can in the greatest detail we can, looking at the nearby stars already, and maybe experiencing the planet search on kind of different environment, a bit older, younger, metal poor, metal rich, high density environment, all this, which has an impact on the formation of the planet. I mean, you can imagine when you have a dense cluster with a lot of supernova, with a lot of major event going on, you essentially blow out any disk. You destroy all the disk just by the fact you have supernova. So supernova is essential because they're making the element that is being used for life later on, but they also, the event also is absolutely destroying everything around. So how far do you need? What do you have a special environment which is better than the others to form life? I think that would be very interesting. So I would tend to look at different environment first before going to back in time a lot and different galaxies. But I know some people are very eager to detect planet on other galaxies, and Andromeda is the obvious galaxy that we should look at.
I like very much this expression. I mean, in all your program is that you kill it ideas. I mean, and I know that this is like that. I mean, in other subjects or related subjects appears like that. I mean, that there are ideas and there are ideas established, but they are not what is happening in nature. So it's very, very interesting the approach you presented in the different chapters. And because after all, I mean, this is connected. I mean, what is the model for formation of planets, for planet formation? I mean, even not exoplanet, I mean, because it's connected. I mean, you answer, I mean, you comment very well on that. I mean, and it's very important to understand the formation of planets in a very clear way. I mean, to have some standard model set as and then to put in all the environments. I mean, as you said, to go to explore, and in your mind, I mean, do you think that there is a model, or in your understanding, updated and clear as you have, that you understood, or you could say planetary formation is more or less controlled, understood, I mean, from physics?
You know, this is an interesting question, because in a way we understand globally the planetary formation. It's a bit like if you ask somebody which is predicting the weather. So we understand it's a Navier-Stokes equation. We know this equation very well. So potentially we understand completely the atmosphere on the Earth and the weather. But still, who can predict the weather more than 1 week in advance? Nobody. Because the branching, the amount of element that can turn over to a different outcome has increased with the time. And that's about the same for planetary formation. I think we understand the big picture. That's the one I described to you. Now, why then do we end up like that and not like that? That may be like the weather, because a little bit of something happened and turn the solution into a direction compared to another one. That's why we tend to see right now the global picture and populations, and trying to understand what is the more likely scenarios, what is the likelihood to end up like that and like that, because it's a bit like the weather. So maybe one day we will understand better that given the condition you had at the beginning, it's more likely you will end up like that. Like you can predict that the weather in England will be more rainy than the weather in Greece. But it can rain in Greece as well, and it can be sunny in England as well. So you see, this is exactly the idea here of the planet formation. So there is this embedded complexity.
Yes, the complexity.
You understand the picture, but it doesn't tell you will know exactly what's going to happen. And we still back to the situation that we are one of the many, and the fact we are having this conversation means life happen on our systems. And maybe we need a system like our own specifically to have life. And this is what I need to understand right now. I need to understand whether life can happen on other systems, or we need exactly to be like on. We need a Jupiter, we need the moon, we need this, we need that, or not. And actually there can be different different origin of life. And that's what we're trying to do, trying to build what's called a universal life model.
Yeah, that
Expanding
is.
a bit this Copernicus revolutions that set the Earth at the right locations. We're trying to set the solar system at the right location, and tomorrow we're going to set life at the right location.
Yes, it's fascinating. I mean, I know all these modern ideas of complexity and physics, I mean, statistical physics, universality, class of universality and complexity, combined with more set detailed, and that need, I mean, these ideas also need to be introduced in for astronomers. I mean, what, and that is not so easy. I mean, of course, you, I mean, that is globally set is real effort and joint effort. I mean, that not all is following, but it's really at the cutting edge that you. So I like very much your explanation. So if I mean I don't want to retain.
Yeah, I have another meeting after. So I
see just
1 minute.
to finish. Try to finish to thank you. So to you heard about of a Chalonge medal, perhaps. It is one of the medal of the school, with which we thank in particular Nobel Prizes who came to the school and were always at the school and make the effort to come and to explain as you. I mean, the Chalonge medal in 91, when the Chalonge school was inaugurated, I offered it to Chandrasekhar, who inaugurated the school with. So this is Chalonge medal, who is exclusively for the school, Hotel de la Monnaie de Paris, the French mint is coined. And in the reverse is the Chalonge, and in the reverse is the upper side, is the mirror of a telescope on which Milky Way is reflected, an Orion constellation, and the downside, the inferior south, is the French Alps, because Chalonge was an alpinist too, and came to Jungfrau-Joch, Swiss Alps, Jungfrau-Joch scientific station to make the observation with his spectrograph and microphotometer. It's a rich history, and it's a rich history in the scientists who got the school. I mean, not but just to mention Bruno Pontecorvo, I mean, who came and supported the schools, Bruno Pontecorvo, Peter Bergman, who postdoc of Einstein, and many others. Peter Bergman, who is here, got this school medal too, and Nobel Prizes in cosmology. I mean, you know, the modern ones. So the other medal is Hector-de-Vega medal, who Hector, who was one of the pivots of the school, theoretical physicist, brilliant, and going, crossing all the, I mean, all branches of physics, and in particular, I mean, in the school, and worked with me and supported. And the reverse side is, I read you in French, Le gentilhomme de la science. L'école Daniel Chalonge reconnaissante la science avec une très grande exigence intellectuelle et un visage humain. Et donc, les recipients of the Chalonge-deVega medal are the ambassadors of the school. Last, I mean, was Barry Barish here in the program. I mean, Reinhard Hensel, Gerard Toft, and in December just Adam Rees. So we are very proud, and the medal is virtual because I hope very much we have the medal for you. and we hope very much we can give the medal. But from today, you are recipients of these two school medals. Thank you very much. We are
Thank
proud.
you very much. Thank you. Merci.
Merci Didier.
Au
À
revoir.
bientôt. Au revoir.
Bravo la Suisse.
C'était
Bravo la
très, très
Suisse.
bien.
Merci.
Merci la Suisse. Bravo la Suisse.
Merci.
À la prochaine.
So goodbye, and we meet in 2 weeks for the next lecture. Thank you. Goodbye.